Okay, in this lecture we're going to start our section 2.5 material on physical applications of the integral. Now throughout this section we're going to be considering several different physical applications. So I'll break up our lectures into small pieces over each type of application that we'll consider. And in this first part we're going to be considering how to determine the mass of some object that has varying density throughout. And in the first part of this section, we'll consider the one-dimensional case that we're working with a thin rod or maybe a wire. So let's consider the following. Consider a thin rod or perhaps a wire which is oriented along the x-axis with its left end at x equals a and its right end at x equals b. So here, to visualize this, let's say we've got our x-axis, and we have some wire whose left end is at x equals a, and whose right end is at x equals b. So we've got a wire, or perhaps a very, very thin rod. Now, over the length of this wire or this rod, we might have varying density from point to point. So let's ask ourselves, if the density of this rod or this wire is varying from point to point, then we might use what's called a linear density function, which is denoted as rho of x, to denote the density of this rod or this wire at any point x. So here, over the length of this rod from x equals a to b, at different values of x, we might have different densities. This object may not be perfectly uniform throughout. It might be a little more dense in some places than others. But the density at any given point we will denote as rho of x. So here, since the density is varying along a line, this is called a linear density function. Now, recall that density is a measure of the mass of an object per unit length here, if we're talking about a one-dimensional cases. What is the mass per unit of length along this wire? So if we're interested in determining the total mass of this rod or this wire from point A to point B, we want to add up these linear density functions times the length of our wire on the intervals where that linear density function is valid from point A to point B. So the idea is similar to what we saw in the earlier sections from chapter 2. We're going to think about slicing up our wire into very small sections of a thin width dx. So essentially, for dx being very, very small, on each of these little sections of wire, we could say that we have a constant density given by rho of x, where x is the length that we're extending along our wire from A to B. So to get the mass of that little section of wire, maybe let me call this the mass of a wire segment, I would take the density of the wire on that very small interval, which we would call rho of x, times the length of that little section of wire, which we would call dx. And to get the total mass of this wire, I want to add up the mass of these little wire segments all the way from x equals a up to x equals b. So here we could say the total mass of the wire would be the sum of these little sections, rho of x dx from x equals a to b, and this process of adding up values of these small sections is given by the definite integral. Here, and we would be integrating from x equals a to x equals b. So we arrive at the following theorem, which we refer to as the mass density formula of a one-dimensional object. So suppose that we're given a thin rod or perhaps a wire oriented along the x-axis on the interval from a to b, and let rho of x denote a linear density function, giving the density of this rod or this wire at a point x within our interval from a to b. So in this case, the total mass of that rod or that wire is given by m, which is the definite integral from a to b of rho of x dx. So let's consider a problem in evaluating the mass of a one-dimensional object of varying density. So here we're told to consider a thin rod oriented along the x-axis on the interval from 1 to 3. And we're told if the density of the rod is given by rho of x equals 2x squared plus 3, what is the mass of this rod? So here, using our new theorem, the mass of this rod would be given by the integral of our linear density function, which was 2x squared plus 3 dx on the interval from 1 to 3. So here, our antiderivative would be a 2/3 x cubed plus 3x, and we're evaluating from x equals 1 to 3. So substituting in 3, we would have 2/3 times 3 cubed, which is 27, plus 3 squared, which is 9. And then we subtract the value we get when we substitute in x equals 1, which would be a 2/3 plus 3. So let's see what we're left with here. So our 2/3 times 27, well, if I cancel one factor of 3, this would be the same as 2 times 9, or 18. Plus 9 would be 27, and then we're subtracting a 3, which would give us 24, and then we're subtracting a 2/3. So simplifying, 24 would be 72/3. We're subtracting 2/3, which leaves us with 70/3 for the mass of this wire. So let's consider a similar problem of evaluating the mass of an object in 2 dimensions, perhaps a thin disk or some plate, which has variable density as we move outward from the center of that plate. So here we will consider a thin disk, essentially like a very thin circular metal plate, of radius r, which is centered at the origin of the xy plane. So if the density of this plate or this disk varies only along its radius, so that is as we move outward from the center, our object might have varying density as we are moving outward from the center, we can make use of a radial density function, rho of x, to denote the density of the disk on any circle of radius x from the center of our disk. So let's try to visualize this problem. Let's suppose that in the xy plane, we have some disk centered at the origin of radius r. And here, this disk might have varying density. So here we've got a solid disk. Let me maybe shade this in to reflect the fact that this is a solid disk or a plate. And this plate might have variable density along its radius. So here our assumption is if the density is varying only along the radius, we can use a radial density function, rho of x, to denote the density on the disk, or of this disk on any circle of radius x from the center. So what I mean by that is on different circles, or circles of different radii, as we're moving outward from the origin, this disk might have different densities on these different circles. And the density of our circle, or of our disk on one of these particular circles, will be denoted as rho of x, where x is the distance that we've moved outward from the origin. So it's the radius of these different circles. So to find the mass of our disk on this one particular circle, so we could say the mass of the disk, let's say segment, well, we could take our radial density function, which is rho of x, that would give the mass per unit length along this circle or around this circle. And then we would multiply by the circumference of that circle. That is the total length or arc length along that section. Now, the circumference of such a circle would be given by 2 pi times the radius of that circle, which is what we were calling x. X is the radius of these circles as we're moving outward from the origin. And if we're choosing these circles of a radius x, or choosing some little segment of my disk that has a radius x, and the thickness of this little disk is what we would call dx, or a very small thickness, then we would need to multiply by dx to get the mass of that little disk segment. Or if we rearrange this slightly, 2 pi x rho of x dx. So in order to get the total mass of this disk, we would want to add up the mass of all these little disk segments from the center of our circle, which was a disk of radius 0, out to the outer edge, which was our disk of radius r. So we would be integrating from 0 to r this expression, 2 pi x times rho of x dx. Or if we pull the factor of 2 pi out in front of the integral, 2 pi times the integral from 0 to r of x rho of x dx. So then we arrive at the following theorem, which is a mass density formula of a circular object. So here, let rho of x be an integrable function which represents the radial density of a disk of radius r. So then the mass of this disk is given by the integral of 2 pi x rho of x dx over the interval from x equals 0 to r. So one comment on some terminology here In the case that we were working with a one-dimensional object oriented along a line, like a wire or a thin rod, the density function was called a linear density function. In this case, we're working with a circular object, and the density varies as the radius of our disk increases. Then that function is called a radial density function instead of a linear density function. So let's look at an example of this. Here we're told to let rho of x equal 3x plus 2 represent the radial density of a disk, and we want to calculate the mass of a disk of radius 2. So using our new theorem, the mass of such a disk is given by 2 pi times the integral from 0 up to the radius of our disk, which we were told is 2, of x times our radial density function, 3x plus 2 dx. So to integrate, I'll first distribute my x, and I have 2 pi times the integral from 0 to 2 of 3x squared plus 2x dx. And the antiderivative is then 2 pi times x cubed plus x squared, which is being evaluated from 0 to 2. So we're left with a 2 pi times, when we evaluate at x equals 2, we have 8 plus the 2 squared is 4. And then we subtract what we get when we substitute in x equals 0, which would be 0. So finally, we have a 2 pi times 12, which would give us a 24 pi for the mass of the disk being described in this problem.